In our previous session, we had discussed about the airfoil data. Let us start off with the lift curve and pressure distribution curve in this session. The graph here indicates that CL varies linearly with alpha over a large range of angle of attack, where CL is the coefficient of lift and alpha is the angle of attack. When alpha is 0, there is still a positive value of coefficient of lift, that is, there is still some lift even when the airfoil is at 0 angle of attack to the flow. This is due to positive camber of the airfoil. All airfoils with such camber have to be pitched to some negative angle of attack before 0 is obtained. For large value of alpha, the linearity of the lift curve breaks down. As alpha has increased beyond a certain value, the CL peaks at some maximum value called CL max and then drops precisely at angle of attack is further increased. In this situation, where lift is rapidly decreasing at high angle of attack, the airfoil is stalled. The phenomenon of airfoil stall is of critical importance in airplane design. It is caused by flow separation on the upper surface of the airfoil. At point 1 on the linear portion of the lift curve, the flow field over the airfoil is attached to the surface. The effect of friction is to slow the airfoil near the surface. In the presence of an adverse pressure gradient, there will be a tendency of the boundary layer to separate from the surface. As the angle of attack is increased, the adverse pressure gradient of the top surface of the airfoil will become stronger, and at some value of alpha, the stalling angle of attack, the flow becomes separated from the top surface. When separation occurs, the lift decreases drastically and drag increases suddenly. This is associated with point 2. This effect can be further demonstrated where the lift curve for a cambered airfoil is compared with that of a symmetric no-camber airfoil. Note that the lift curve for a symmetric airfoil goes through the origin. So we can say by this comparison that cambered airfoil generates more lift at 0 angle of attack than a symmetrical lift, and it is more efficiently used in aircraft. The aerodynamic performance of airfoil section can be studied most easily by reference to the distribution of pressure over the airfoil. Various parts of the pressure distribution are depicted in the figure here. The upper surface is lower, plotted higher on usual scheme than the lower surface coefficient of pressure in this case, but it does not have to be. The lower surface sometimes carries a positive pressure, but at many design conditions is usually pulling the wing downward. In this case, some suction, which has negative coefficient of pressure, downward force or lower surface is present near the midcord. Pressure recovery is the region of the pressure distribution where the pressure increases from its minimum value to the value at the trailing edge. This area is also known as the region of adverse pressure gradient. As discussed in other sessions, the adverse pressure gradient is associated with boundary layer transition and possibly separation if the gradient is too severe. Trailing edge pressure is the pressure at the trailing edge is related to the airfoil thickness and shape near the trailing edge. For thick airfoil, the pressure here is slightly positive. The velocity is this bit less than the free stream velocity. For infinitely thin sections, coefficient of pressure is 0 at the trailing edge. Large positive value of coefficient of pressure at the trailing edge imply more severe adverse pressure gradient. The CL and CP is the section lift coefficient is related to the coefficient of pressure by the difference. Stagnation point occurs near the leading edge. It is the place at which velocity is equal to 0. Note that in incompressible flow, coefficient of pressure is 1 at this point. In compressible flow, it may be somewhat larger. We can get more intuitive picture of the pressure distribution by looking at some examples which were done in our previous courses. Now the answer to the exercise. To create a tabular column, I hope you all would have worked on it, and this is your answer. So NACA 1016 has a maximum thickness of 17.5% located at 41.8% of the chord. The maximum camber is 0 and maximum L by CD is 39.2 and the angle of attack is 5 degrees. So the type of airfoil is symmetrical because there is no camber present. NACA 4412 has a maximum thickness of 12, located at 30% of the chord and has a maximum located at 40% of the chord has a maximum CL by CD of 56.1 at an angle of 8.5, and it is a camber airfoil. Like this, I hope you can cross-verify your answers with this table and check whether you have got it correct or not. So basically, we have 3 symmetrical and 3 camber airfoil. I hope you would have understood today's session. Let us move on wings in our next session. Thank you.